Hey guys, today we're going to talk about the Lagrange error bound. So we have seen error bound for an alternating series, and we see how that works. But the Lagrange error bound will handle the error bound for any series, whether it's alternating or not. And we'll begin by talking about Taylor's theorem with remainder, whatever that means. So let's talk about that. So we probably remember that we could write a function as an infinite series, although if you look closely, I haven't written this as an infinite series. More about that in a second. But we remember the structure, right? So this is f of a, but it's really the 0th derivative at a over 0 factorial times x minus a to the 0, which becomes f of a. This is really the first derivative at a over 1 factorial times x minus a to the first. The second derivative at a over 2 factorial times x minus a to the second, and then we get the pattern from there. But the way I've written it, we're actually stopping here at the nth derivative of a over n factorial times x minus a to the n. In other words, this is a truncated series. It's not all the terms. And as we know, you're not going to be equivalent to the function unless you have every single term going to infinity. So this is really not at all equal to this. It might be close to it, so I should have put a wavy equal sign here, right? But I'm going to keep the equal sign here and add just one thing onto the end of this so that it is going to be equal to this. And I'm going to write this. I'm going to add the n plus 1th derivative, so the n plus 1th derivative evaluated at z over n plus 1 factorial times x minus a to the n plus 1. And then I'm going to stop there. And if I do, this is going to be equal to this. And this term that I've written here is known as the remainder. And here's why. Because you should think of this term right here as really not just one term. This is like we stopped here, right? Let's say we went 6 terms in or whatever. We know we'd have to add in all of the rest of them to be equal. So this term is really equivalent to the sum of the remaining terms. And that's why it's called the remainder. So this right here is called the remainder. But we can also think of it as the exact error, right? Notice the exact error, because let's say we go 6 terms in, right? We know we're not equal to this, but if I add this mystery remainder over here, then I will be equal to this. So this is our exact error. So we could say this. We'll say the exact error is equal to this crazy term over here, the n plus 1th derivative at z over n plus 1 factorial times x minus a to the n plus 1. So this seems pretty awesome because if I can get this, right, that is beautiful because then I can get the exact value of this, right? I don't have to estimate. I can just add this and get the exact value. But of course, it's not that simple because this, hopefully you realize, is not the next term, right? Because there's a whole bunch of terms after it. But if I made one small change to this, it would be the next term. The next term after this one would be if this was the n plus 1th derivative evaluated at a. But I have this mysterious z here. And therein lies the problem, because we don't know what z is. Unfortunately, right? If we did, that would be great. But although we don't know what z is, we know something about z, and this is key. So even though we don't know what z is, whatever this mysterious value is, we know something about it. So z is going to be between a, the center of your series, and x. And x is the value at which you're evaluating or estimating. So this is going to be important for us to know as we move forward with this. We don't know what z is. But what we do know about it is that it's between a and x. So that's what we have to remember here when we get to what we're going to call the error bound. Again, if we knew what z was, we wouldn't just get an error bound, we would get the exact error, right? So what is the error bound? Well, it's related to this. And here's what it's going to be. So the error bound, known as the Lagrange error bound, is going to be what? Well, we have this mysterious number z. We know it's between a and x. What we're going to do is maximize this value, right? We're going to get the most that this could possibly be, just this part right here, the n plus 1th derivative at z. And if I can figure out what that is at most, then we're going to get what we call the error bound, right? So it's going to be the absolute value of, and this part right here, I'll write it in a different color to make it clear that it's the special part. It is the n plus 1th derivative at z. But I'm going to say max and the rest of it over n plus 1 factorial times x minus a to the n plus 1. So this is the key, right? We're not actually going to get the n plus 1th derivative at this mysterious z value. But what we're going to do is maximize this. So I'm going to say we know z is this range between a and x. Okay, let's maximize this number right here, and that is what's going to give us the error bound. Again, if we actually had z, we would get this thing called the exact error. Okay, let's see how this works. First, let's start with something familiar. So we have f of x, if f of x equals 1 over 1 minus x, we want to estimate f of 1/5 with a 3rd degree Taylor polynomial. Okay, so this is one of those Maclaurin series we're supposed to know. So 1 over 1 minus x, you might remember this is the first one I think we ever looked at. This one is 1 plus x squared plus x cubed plus dot 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 plus x to the n, and then on forever. We saw this, we were amazed. It does have that smaller interval of convergence, but still pretty amazing stuff here. And speaking of that interval of convergence, 1/5 is within that interval of convergence. That's why we can estimate f of 1/5 using this. So it says to use it with a 3rd degree Taylor polynomial. So the 3rd degree Taylor polynomial is going to be this. It's going to be the terms up to there, right? X cubed. So 1 plus x squared plus x cubed. So the 3rd degree Taylor polynomial evaluated at 1/5 is going to be 1 plus 1/5 plus 1/5 squared plus 1/5 to the 3rd. So our 3rd degree estimate is going to be equal to 1. Actually, let's write it all with, no, let's write it. 1 plus 1/5, and then plus 1 over 25, and then 1 over 125. Okay, now let's write them all with a common denominator, which of course is 125. So we have 125 over 125 plus 25 over 125. There's your 1/5. Plus 5 over 125. There's your 1/25. And then 1 over 125. All right, so what do we get here? So our 3rd degree Taylor polynomial estimate for f of 1/5 is 156 over 125. And by the way, 156 over 125 gives you a number like 1.248. Okay? Now, we know that we could actually, of course, this is a pretty easy function to plug a number into. If you actually plugged in 1/5 here, you get 1 minus 1/5, which is 1 over 4/5, which is 5/4, right? And 5/4 is 1 1/4, or 1.25. So not bad, right? 1.248. But our goal is going to be to find that error bound. Now, yesterday we were doing the alternating series error bound, where it was simply the first neglected term. You could probably realize why that's not going to work here, right? The next term after this would be 1 over 625. That's clearly not going to be the error bound here because all the terms are positive, right? So if I add 1 over 625, I have to add in some more stuff after that to get to the actual value of f of 1/5. So that's not going to be the error bound, right? That's going to be smaller than the actual error, right? Your error bound is always going to be larger than your actual error, right? Because it's the most your error could possibly be. So clearly that first neglected term stuff does not work with a non-alternating series like we have here. So how do we get this mysterious error bound here? All right, well, here's what we know. We have this expression, which is the absolute value of, let's write it here, our error bound is equal to the absolute value of the n plus 1th derivative, evaluated at mystery number z, but we're going to say we're going to maximize this, and then over n plus 1 factorial times x minus a to the n plus 1. And that's going to be our error bound, right? So let's see if we can work through this to somehow arrive at our error bound here. Now, first of all, what's a? Well, clearly we're centering at 0 here, right? These are all a whole bunch of x minus zeros. So our center a is 0 here. Our value of x is the value of what we're evaluating at. No, that didn't come out quite right, but you get the idea. It's 1/5 in our case, right? X is the value you're plugging in for x when you're doing your estimate. So x is 1/5. So that's important because what we said before was, even though we don't know what that value of z was, we do know something about it, and that it's between 0 and 1/5. But now I need to know what this n plus 1th derivative is. Well, my value of n here, right, since we stopped here, n is 3, right? So we can see that we stopped at that term, so our value of n is 3. So n plus 1 is clearly 4. So this is really the 4th derivative evaluated at z, or at least the maximum value of that. That's really what we need to find in order to figure out the rest of this. Okay, so let's see if we can actually do it. Now, in order to get the 4th derivative at z, I need the 4th derivative, right? So it's a time to find a whole bunch of derivatives. So let's launch into finding those derivatives. So first, the 0th derivative, otherwise known as the function. We can see that that's just 1 minus x to the negative 1. There it is. The first derivative, that's negative 1 times 1 minus x to the negative 2 times negative 1. So in other words, 1 minus x to the negative 2. The second derivative is going to be negative 2 times 1 minus x to the negative 3 times negative 1 with the chain rule. So that's going to be positive 2 times 1 minus x to the negative 3. And the next one is the one we actually, we got to do 2 more to get to the one we need, right? Because we need the 4th derivative. All right, so we have negative 6 times 1 minus x to the negative 4 times negative 1. So this is 6 times 1 minus x to the negative 4. And now we can get to the one we want, the 4th derivative. So the 4th derivative at x is negative 24 times 1 minus x to the negative 5th times negative 1. So in other words, positive 24 times 1 minus x to the negative 5th. So our 4th derivative at x is 24 over 1 minus x to the 5th. So we have to do the 4th derivative at z, right? Well, 4th derivative at z, I think we got that. The 4th derivative at z is going to be 24 over 1 minus x to the 5th Oh, sorry, that's the fourth derivative at x. 1 minus z to the fifth, right? You're doing the fourth derivative at z, so 1 minus z to the fifth. Okay, let's see where we can go from here. All right, so we're looking for this error bound. And it's going to be the absolute value of, okay, now we know we're looking at the fourth derivative as z, the maximum of that, right? So it's really 24 over 1 minus z to the fifth, but it's the maximum of that. That's what we really want there. Over n plus 1 factorial. So remember, n for us was 3, right? I think I erased it, but yeah, n was 3 for us. So this is going to be over 4 factorial times x minus a. And again, a is 0, right? We're centered at 0, so it's really just x here. Raised to the n plus 1. Again, for us, n was 3, since we went 3 terms in, right? So n plus 1 is 4, so x to the fourth. Okay, so our error bound is going to be, let's see. So we have our error bound. It's the absolute value of, okay, now here's the deal. We want to get the maximum possible value for this. What do we know about z? Well, z is between those two guys, 0 and 1/5. That's what we know about z. It's some number between 0 and 1/5. So what value in that range from 0 to 1/5 would maximize this fraction right here? What would do it? Well, if I plugged in 0, I'd have 24 over 1. If I plugged in 1/5, the other extreme of this interval from 0 to 1/5, if I plug that in, I'd have 4/5 to the fifth, right, which is a number less than 1 raised to the fifth. So it's 24 instead of divided by 1, 24 divided by a number less than 1, which of course is larger, right? So we're going to maximize this if z is equal to 1/5. So we're going to let z equal 1/5. Again, z is not 1/5. We don't know what z is. If we did, we'd get the exact error. But if z was 1/5, we're going to get the largest this could possibly be. In other words, our error bound. So we're going to let z equal 1/5. So that leaves us with 24 over 1 minus 1/5 raised to the fifth. And that's our maximum value of this, based on our restriction on z. So this is over 4 factorial times, now x. What's x? Well, x is 1/5. That's the number we're plugging in to estimate, right? 1/5. So that's going to be times 1/5 to the fourth. Now, I will tell you that these problems on the AP exam are, yeah, I was going to say almost always, but it is always in the non-calculator part of the test. Always. They never put this in the calculator part. They're expecting to do this kind of stuff without a calculator. So let's see if we can, manage our way through this, I guess. All right, so what do we have so far? So we have 24 over 4/5. There's your 1 minus 1/5 to the fifth. Times 1/5 to the fourth. And it's all over 4 factorial. Okay, so we can kind of do a keep change flip here, right? So this is really like 24 times 5/4 to the fifth times 1/5 to the fourth. And this is like over, really all over 4 factorial. Now, if it looks scary and it's like, oh man, I can't do that without a calculator, you can. It's actually kind of fun to do this. Because we're going to kind of break this up. It's like, this is 5 to the fifth over 4 to the fifth. So my 4 to the fifth will end up in the denominator, 5 to the fifth in the numerator. This is 1 to the fourth. That'll stay in the numerator, but then I have 5 to the fourth. We'll put that in the denominator. So let's have fun with this. We're going to have 24 times 5 to the fifth remains in the numerator. So 5 times 5 times 5 times 5 times 5. So there's your 24, and then 5 to the fifth. Now that 4 to the 1/5 is going to end up down here. So 4 times 4 times 4 times 4 times 4. This 5 to the 4th will also end up down here. So times 5. So 4 of these 5s. And of course, in the denominator, we also have our friend 4 factorial. 4 times 3 times 2 times 1. Now the fun part. We know when things are multiplying on the top and multiplying on the bottom, we can cancel. So let's do it. This 5 and this 5, this 5 and this 5, this 5 and this 5, this 5 and this 5. We're having fun already. And I recognize 4 times 3 times 2 times 1, that's 24, right? So this 24 takes care of this. I guess we can take care of the 1 too. So we're just left with this. What is this? I think we can figure it out. This is going to be, obviously it's a positive number, so it's going to be 5 in the numerator, and then 4 times 4 times 4 times 4 times 4. So 4, 16, 64, 256, and then 256 times 4, 1024. We don't need no stinking calculator. So there it is, 5 over 1024. And again, what is that? It's the error bound. It's not what we're off by, but it's what we're off by at most, right? And if you actually take a look, 5 over 1024, that's equivalent to, let's see, get the handy calculator out here. We do 5 divided by 1024, it's like 0.00488, something like that. And like we said, if you actually do f of 1/5 and you plug it in here, you're going to get 1.25. So what was our actual error? The actual error, just to compare it, was, well, it's going to be what? That absolute value of f of 1/5 minus what our estimate, our third-degree Taylor polynomial was at 1/5. Again, it doesn't matter the order if we put it in absolute value. F of 1/5 we know is 1.25. So absolute value of 1.25 minus our estimate, which was 1.248. So the actual error here was 0.002. That's the actual error. I shouldn't really be circling it because what matters is our error bound here. But so the actual error is 0.002. What matters is our error bound makes sense because what we're saying is this is the most we could be off by. And we were, in fact, off by less than that. So this is the error bound on our estimate. So this is the Lagrange error bound. Let's do one more example coming your way next. As promised, another example. Here we go. So we want to estimate 1 over e, the value of 1 over e, with a 4th degree Taylor polynomial and find the error bound. Okay, so 1 over e. Well, we're supposed to know the Maclaurin series for e to the x. And by the way, a real question would be much more detailed than this because we need to know, okay, do you want that 4th degree Taylor polynomial centered at 2? Do you want it centered at 5, right? Obviously, we're doing one centered at 0 since we know the Maclaurin series here. So what was that Maclaurin series again? I think it was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus on, x to the n over n factorial. If we went all the way out to infinity, we would get e to the x. And this one actually converged for all x. But let's take a look at the 4th degree Taylor polynomial here. So that would be 1 plus x squared over 2 plus x cubed over 3 factorial, which is 6. And we're going to the 4th degree here, so our 4th order Taylor polynomial, over 4 factorial, that's 20. So I know my 4th degree Taylor polynomial evaluated at something. Well, what am I going to evaluate here, right? I got e to the x is sort of equal to this, right? We truncated it. So we want 1 over e. Obviously, that's e to the negative 1. So we're doing the 4th degree Taylor polynomial evaluated at x equals negative 1, right? E to the negative 1. In other words, 1 over e. So we have 1, and then plus a negative 1, plus a negative 1 squared over 2, plus a negative 1 cubed over 6 plus a negative 1 to the 4th over 24. So this is, well, 1 minus 1, that's 0 right there. So this is really the first well, it's not the first non-zero term, but these contribute 0. So I'm going to write the next term, which is a half, positive a half. And then we have negative 1 cubed, that's a minus, right? So minus a 6. And then negative 1 to the 4th is positive 1 over 24. All right, so we'll add these fractions together with a common denominator of 24. 1/2 is 12 over 24. 1/6 is 4 over 24. So 12 minus 4 is 8, plus 1 is 9. So we have 9/24, which is the same as the 3/8. So our estimate for 1 over e is 3/8. So we think that 1 over e is kind of close to 3/8 maybe, right? So let's figure out what the error bound would be here. All right, so that's our estimate for 1 over e. It's 3 over 8. 3/8. Okay, I want to know how close that is, so we look for the error bound. So the error bound is going to be the absolute value of the n plus 1th derivative evaluated at z, or at least the maximum possible value of that, over n plus 1 factorial times x minus a to the n plus 1. Once again, we're using a Lagrange series here, so a is 0. We're centering at 0. So our value of a is 0. The value of x, what we're plugging in and estimating at, is negative 1, right? So our x is negative 1. Okay, now we need the n plus 1th derivative evaluated at z. Well, our value of n, since we did the 4th degree Taylor polynomial, we stopped at that x to the 4th over 4 factorial, right? So our n is 4 here, right? So our n is 4. So what do we got? We know our error bound is going to be equal to the absolute value of, well, n is 4, so it'll be the 5th derivative evaluated at z, or at least the maximum possible value for the 5th derivative evaluated at z, over n plus 1 factorial. Again, n is 4, so over 5 factorial. A is 0, so it's just x to the 5th. Okay, so we need the 5th derivative. So now is all the derivatives, which here is actually not bad at all. F of x is equal to e to the x. F prime of x is equal to e to the x. We jump right to the 5th derivative, and that's e to the x. So the 5th derivative of z is equal to e to the z. Gee, that was easy. Okay, so we have this over here. All right, so yeah, I guess I can erase what we have here. Yeah, okay, I'll do that. Okay, so here's what we got. We have the absolute value of e to the z, or the maximum possible value of that, over our 5 factorial times our x to the 5th. Well, x is negative 1, right? So negative 1 to the 5th. Okay, so z is between these two guys, right? So we need to recognize that. So I'll write it over here. Z is between a and x. Again, we're centering at 0. X here is negative 1. So z must be between negative 1 and 0. So we're going to choose a value in that range from negative 1 to 0. Usually we focus on the extremes to see which will be the largest for e to the z. Well, if z was 0, this would be 1. If z was negative 1, this would be 1 over e. So clearly, the largest is when z is 0, right? So I'm going to choose z as 0 here. So we'll do that. These here. So here's where we're at with our error bound at this point. So we're going to use 0 there. That's the maximum possible value of e to the z, knowing that z is between negative 1 and 0. Over 5 factorial times negative 1 to the 5th. Well, e to the 0, of course, is just 1. So the error bound here turns out to be the absolute value of, well, negative 1 to the 5th, that's a negative 1. But we're taking the absolute value anyway, so this is really just 1 over 5 factorial. So the error bound is equal to 1 over 5 times 4 times 3 times 2 times 1. What is that? 20. So that's 120. And that's our error bound. And remember, that doesn't mean we're off by 1 over 120. It means we're off by less than that. Right? This is a bound on our error right here. So not bad. This is not a bad estimate for 1 over e. And you could, I'll leave an exercise to you on your own to see what 1 over e is and see how close this is. Of course, this is 0.375. So 1 over e should be in the neighborhood of 0.375 because we're not going to be off by more than that. That's our error bound. But if you were paying attention here, you might have realized something. So the Lagrange error bound does a great job of getting us that error bound. But what did the series really look like when we plugged in -1, right? So we're saying our e to the -1 was approximately equal to 1 minus 1 plus, and the next term was -1 to the second power, that's a positive, a half, and then this would be minus 1/6 plus, and the next term after this would have been, actually we went this far, right? 1 over 24, I think. And of course, if we stop there, e to the -1 we're saying is approximately equal to this value. That's how we got our 3/8. But what we notice about this is that it's an alternating series. And if it's an alternating series, you don't have to worry about all this mess with the n+1th derivative at z and maximizing all that stuff. You don't have to worry about doing the full Lagrange error bound. All you have to do, if it's alternating, is look at that first neglected term. What would that first, or the absolute value of it, right? What would that next term be? Well, the next term would have been 1 over, well, this is 3 factorial, 4 factorial, 1 over 5 factorial, which of course is 1 over 120 there. So the absolute value of that is 1 over 120. So the error bound is simply the first neglected term here because it's an alternating series. So the Lagrange error bound always works. But if it's alternating, you want to take advantage of that and just look at the absolute value of that first neglected term.